Good afternoon to everyone, and welcome to this MOX colloquium by Mark GENTON, Professor Mark GENTON.
So thank you, Laura, very much for inviting me, and thanks to all of you for coming to my presentation. Indeed, today I'm going to talk about this story. For the past 8 years, with my group, I've been working on exascale geostatistics for environmental data science. Before I do that, I just wanted to show you a picture of the group at KAUST, currently in Saudi Arabia. We're about 80 in statistics. The picture was taken about 2 years ago. But of course, things didn't start like this. In fact, when I joined in 2012, my group was, well, just myself, basically. I was the only statistician there. And little by little, I recruited some, well, quite outstanding faculty whose picture are presented here. And then in 2017, we were enough to start a program in statistics, so officially such a program. And now we are 9 core faculty. The latest is the first Italian statistician we have, Maurizio Filippone, and he works on Bayesian deep learning. I have a research scientist, Sameh Abdullah, who's affiliated with the Extreme Computing Research Center at KAUST and has been quite fundamental in the development of the project I'm going to present. So here's an outline of my presentation. There will be 4 parts. In the first one, I will present what I call some fundamental problem in spatial data science. And I will tell you how this problem becomes very challenging when the size of the data set becomes large. And this will lead to the second part that motivated the development of this software, ExaGeoStat, for large-scale spatial data science. This software has allowed us to run international competition for spatial statistics. So that will be the third part. And briefly, in the fourth part, I wanted to tell you a little bit about the very latest research we've been working on, namely exascale climate emulators that are related to the previous topics, as you will see. So let's start with some of these fundamental problems. So in spatial data science, we deal with spatial data. So this means that the data have associated a location in space. So on the top left figure, you see a picture taken from a satellite on a specific day about sea surface temperature. And this is taken around South Africa. And the idea is that we want to fill some of these white gaps. So some of these white gaps come from the fact that the satellite don't cover every part. So there is some empty spots here, but also there are some other ones that come from cloud cover. And we would like to fill basically this, the white part of the image. And what we do in spatial data science is to use this law of geography that tells us that nearby things tend to be more alike than those far apart. So the idea is that if you measure temperature at 2 locations that are close to each other, they tend to be similar or related in some way, whereas if they are far away, they are less related. In the image on the top left, there are about 20,000 locations. So this is not very large, but it starts to be still a good size for the data. On the bottom 2 pictures, another type of problem I'm interested in is for wind energy, especially over Saudi Arabia, where there are very few wind farms. And so the question is, where should we put this wind farm? So if you use, well, there are almost no monitors or very few monitors. So the data that we can get are from climate models. So on the left picture, you have an average wind speed map for this period from 2009 to 2014. And this is from a classical model. The resolution is 1 degree by 1 degree. So this means that in 1 pixel, where you have information about the wind, the size is 100 kilometer by 100 kilometers. So this is much too big to really infer anything about a wind farm scale. So then what we can do is to run a regional climate model at higher resolution. This is what you have on the right here at the 5 kilometer resolution. And you start to see now many more details related to the topography of the country. And this is the kind of data we would like to use. But in this case, over Saudi Arabia, there are about 500,000 locations. So this starts to be big, right? So this is the general context I'm interested in. So here's the first type of classical problem, namely spatial Gaussian likelihood inference. So assume that we observe a variable z, say temperature, at n location in space, S1, S2, up to Sn. They can be irregularly spaced over a certain region. And we model the spatial dependent structure with this famous Matern spatial covariance function, which is described here. And the entry ij of a covariance matrix sigma, which will be of dimension n by n because we have n location in space, will be given exactly by this Matern covariance, which has 4 parameters. Sigma square here is called the partial CIL. There's a range beta parameter in the denominator that tells us how quickly the covariance dies with the distance, so the norm of the distance, the norm of the difference between 2 locations Si and Sj. We have a smoothness parameter nu here that appears here and as the order of this Bessel function. And we have a nugget effect tau square such that the variance of the process is actually sigma square plus tau square. Now, if we want to estimate these 4 parameters from the data, we could write the spatial Gaussian log likelihood, which is described here in this red box. And so theta is a 4-dimensional vector of these 4 parameters. The covariance matrix is a function of theta, and we want to maximize this log likelihood as a function of theta. You see that the covariance matrix sigma appears as the log determinant of sigma, and there's a quadratic form in sigma inverse here. So typically, to evaluate this log likelihood, you would have to compute a Cholesky factorization of the covariance matrix sigma. Sigma is, by construction, with this Matern covariance function, a symmetric matrix and positive definite. But this Cholesky factorization will require of order n cube operation and n square memory. So when n, the number of locations, becomes large, then this becomes a very challenging problem to just evaluate this log likelihood function. A second fundamental problem is the one of spatial kriging or spatial interpolation. So this is basically, once you have n observation, how do you predict your variable of interest, say temperature, at m new locations? So you could think about it in the following way. This vector z is split into 2 parts, z1, z2. z1 is of dimension n. This is what you're going to have observed. And z2 is of dimension m. This is the m new location where you want to predict your variable of interest. You model them as coming from a multivariate normal distribution, a Gaussian distribution. You split the mean vector and the covariance matrix accordingly to the dimension n and m. And then, given z1, so given this n observation, you can compute this conditional distribution of z2 given z1. And we know from multivariate Gaussian theory that this is still multivariate normal, now of dimension m, has a conditional mean and a conditional variance. The conditional mean can be used to do the kriging, so the spatial interpolation. And the conditional covariance matrix can be used for uncertainty quantification. Here again, if you look at this expression in red, you see there's this sigma 1, inverse that appear, and there's a multiplication with sigma to 1. And when n and or m are going to be large, this is going to be, again, computationally challenging. The third problem is the one of simulation. So we want to simulate realization from Gaussian random field with one of these covariance model. We can do the simulation unconditionally or conditionally. Unconditionally is simply given a certain covariance function, we can build the covariance matrix sigma, we compute a Cholesky factorization, and if the vector y has ID normal 0, 1 entries, we know through this quantity that z will have the multivariate Gaussian distribution that we wish. The conditional version is that if you have now observed n values that we'll put in Z1, this is the same equation as before, but what we want to do is to simulate from this multivariate normal distribution of dimension m. So we'll need a Cholesky factorization of this matrix. And once again, when n, m are large, this will be computationally challenging. To give you some idea about realization of Gaussian random field with this Mattern model, here are 12 realizations on the unit square with different values of the parameters. So what happens is when you move from left to right, you go from rough field to much smoother field. So this one here, for example, is very smooth, the realization. And when you go from top to bottom, you move from short dependence to strong dependence, which means that, for example, here, if you have an area in red, it's red for a short distance, whereas here with strong dependence, once it's red, is red for a much longer distance in space. Okay, so these are some of the realization from such models. A fourth type of fundamental problem is to compute multivariate Gaussian probabilities. So this appears in a number of problems. For instance, if you're interested in this problem of wind farming, this wind turbine, they will produce electricity once the blades start to rotate. But if the wind is not strong enough, they will not rotate. So there is a threshold, depending on the wind turbine, for example, here of 4 meters per second, after which the turbines start to rotate and produce electricity. So in this type of problem, so we want to find or predict at new location whether we're going to have enough wind speed to produce electricity. In this kind of problem, very naturally, what appears are these so-called multivariate Gaussian probabilities. So it's the integral of the multivariate Gaussian PDF density that we've seen before. This integral is n-dimensional. So this is why here I have an index n. And as you can imagine, if n is large, this is going to be also challenging to evaluate. This appears, in fact, in a number of problems. Those of you interested in Bayesian probability regression, Daniele Durante, who's at Bocconi here, has in his a couple of years ago Biometrica paper shown that, in fact, if you put a Gaussian prior on the probability regression parameter, the posterior is going to have a so-called skew normal distribution or SUN that was proposed by and studied by Adelchi Azzalini in Padova. And the density there of the SUN distribution is of this form, n-dimensional PDF times n-dimensional CDF. So exactly this form. So for this kind of problem there as well, computing these probabilities are challenging. And the fifth of the fundamental problem in my list here is to worry about robustness. So if you have outliers in the data, if you have unusual observation, then what can you do? In the spatial setting, things are a bit more challenging because the position of these outliers in space matter. And so you would have to adapt traditional robust statistic procedure to this spatial dependence. And one kind of simple modification of the likelihood is the so-called maximum LQ likelihood estimator for Gaussian random field. The form, so here I'm assuming that I have some replicates, also capital R of them, so that's why I have this sum. Now I have a function LQ of that Gaussian density we saw before, and LQ depends on this parameter Q. It's just the log if Q equal 1, so it's the usual likelihood in that case. But if Q is between 0 and 1, it takes this form, and one can show that the effect of that transformation on the density will downweigh the effect of outliers from the data, and so bring some robustness. So now you can see that in this kind of setting, this is even more computationally challenging because you have the n-dimensional density, you have R replicates, and if you want to tune this parameter Q, then possibly you have to evaluate this function for many values of Q. So just to summarize this first part, I described these 5 type of problem that appear quite naturally in spatial data science. All of them involve this covariance matrix sigma that tends to be big if you have large data sets. And all of them require a Cholesky factorization of this covariance matrix sigma, so they have this common theme. Notice that here, everything has been described in the Gaussian case, but there are many possible extensions. So these are kind of cornerstone problem to more difficult problem, either trying to get non-Gaussian model through some transformations or adding time to space as well. So if there's space and time, that covariance matrix will be even further increased in dimension. Or here I described everything in the univariate case where you have just one variable, but if you have p variable, then the covariance matrix will be even bigger, right? So even in this very simple case, things are quite challenging. So let me move now to the second part that is about the software ExaGeoStat we've been developing and how it has been developed to address this large scale problem. So again, if you want to do exact computation of this Cholesky factorization, the order is n cube in operation and n square in memory. So high performance computing, or HPC, can bring some help and light when n is large. And this was the motivation to develop this software ExaGeoStat. You can download the software at these GitHubs. So there's a C version, the basic version. There's an R version for statisticians who like to use R. And now we have also a C++ version that is a bit more user-friendly if you want to modify the covariance. If it's not the Matern or not one of the space-time or multivariate model that we have implemented, you can basically build your own as well. Now notice that if, say, you have n equal 1,000,000 location in space, then this order n cube is going to be 10 to the power 18. So this is 1 billion billions. So it's a very big number. And we're going to go back to this type of scale. So the software ExaGeoStat has been designed exactly to address the 5 problems I described earlier on. And of course, there are many approximation methods that have been proposed in the literature to avoid doing this exact computation. The idea here is that if we can do exact approximation, I mean, in some cases, why not? But also, we want to use this software to test this approximation method. So this is why we run these 3 competitions for large data set in spatial statistics to investigate approximation method and compare them on a more fair footage. So basically, the idea is that we ask people worldwide to basically, we generated data set with the exact method from the software. We ask people from the world to try their best method on the data set to achieve certain tasks. And then we rank this method. And so this data set are publicly available as benchmarks. So anyone can try their method on the data set. We have the rank of all the people who tried. And now if someone comes with a new method and say, well, this is a fantastic new method that works great, instead of just trying it on one data set that nobody has heard of or cannot really compare, these people can try it on the data set that are publicly available. And if they rank better than what we've seen, then they have a very strong case that indeed the method is quite good. And I think this idea of running competition to solve certain problem can be open to other subfield of statistics or science in general. Okay, so what is HPC? What is high performance computing? So it's basically using advanced computing technique and technology to solve a complex problem in general, and that requires significant computational power. This system can have multiple processors. They can have accelerators such as GPUs. And typically, the term HPC is used for systems that function above a teraflop or order 10 to the power 18. if we go back to this 10 to the power 18, this is called an exaflop, or this is the exascale. So this is what we want to reach. So a natural question is, are there computers that can work at that speed? Before answering that question, well, it's useful to talk about modern hardware architecture. Basically, two ideas that you may know is to look at either shared memory or distributed memory system. So in shared memory system, you have a setting like this. So this is what is traditionally called parallel computing. You have different processors and they access the same shared memory. Whereas in distributed system, each processor has its own memory. They can communicate among each other. And if that network is fast enough, then this can scale to possibly millions of CPU cores. And the benefit of that is the scalability, the reliability, and the performance of the system, with, of course, the challenge of having a more complex architecture to deal with. So what are the computers that can run at exascale 10 to the power 18? Well, there's a list of, well, those are supercomputers. And I should just say also here that distributed memory system are, for example, a cluster that you may have, but also a supercomputer. So what are the top supercomputers? They are listed at this website. The list is updated twice a year in June and once in November. They are linked to conferences. And on the latest June 2024 list, the top one was Frontier at Oak Ridge National Laboratory. It has more than 8 million cores, and you see that it should work at 1.6 exaflops. You have Aurora, which is at Argonne National Laboratory. You have Eagle, and you have Fugaku in Japan. And now here you have two pictures, Frontier, so the top supercomputer of the world, here on the left, and on the right, Fugaku. So these are very big machines. They take a lot of space. They cost a lot of money, as you can see for Fugaku well. But you can think about a supercomputer like Fugaku as having 20 million smartphones in a single room that you can use, or 300,000 servers at your disposition. So what we've been trying to do is basically to marry these two fields of statistics and HPC, and we call this high-performance statistical computing, or HPSC. You can do this with many subfields of statistics, and one example is to do it in this spatial data science, and this was the motivation to develop this software ExaGeoStat. So in this picture, you see a little bit a description of what we're trying to do. On the top, you have the application of interest related to climate, weather, environmental problem in general, where we want to do modeling, inference, prediction. Often we need also optimization in this likelihood type problems. And all of them, they relate to this Cholesky factorization. So that's really the core of the software. And what we're going to do, if you think about this big covariance matrix sigma that we had before, we're going to divide it into tiles. So if this is one of these covariance matrix, you see here it's divided into 4 by 4 tiles. Each tile, the size needs to be tuned for optimality on the particular hardware that you have. And then you can describe the different operations that you need to do to perform the Cholesky factorization. So these operations are color-coded here. So you go from here to until you get the Cholesky factorization with different operations that you can describe in this tag. And this direct acyclic graph tells you, in fact, the parallelization. For example, these 3 operations in red can be done in parallel, and so on. Now, coding this kind of tile-based algorithm on different systems can be very complicated or need different skills or programming skills. But we can rely on what are called dynamic runtime systems. So here there are 2 that we have been using. StarPU is a group in Bordeaux in France, and Parsec in the US that have developed this runtime system. So basically what they will do is to abstract all this implementation for you. So they will, on a given system, you will say how many GPUs, how many CPUs you have, and it's going to distribute the different tasks to these GPUs and CPUs in an optimal way. So basically, as the user, you don't need to worry about all this detail. This is completely abstracted. And this means that then, so you don't need to do all this coding in MPI or other type of codings, and you can run on shared or distributed system. You can use GPUs or CPUs. You don't worry about this very low-level part down there. So this means that the software is extremely portable. So you can, I mean, this software is not restricted to supercomputer. You can run it on your laptop, you can run it on your desktop, on a cluster that you may have, but it runs also on supercomputers. So on the left, we have the different CPUs and GPUs that we have run the software on. On the right, you have some of the supercomputer that we have run on. So Frontier is number one. Fugaku, in fact, in Fugaku, we run on that system in 2022 when it was ranked number one. So things change quickly over the year. In Italy, you have Leonardo, which is number 6. At Chaos, now we have Shaheen 3 that is ranked number 20. So I think I will skip some of this detail. I will make the slide available if you want to read more detail, but the big picture I gave you, basically we use this dynamic runtime system to abstract all the details to the user. We use this idea of tile-based linear algebra. So many operations have been optimized on different processors, GPUs, based on this tile algorithm. We can do also some approximations. We have the exact version that is tile-based, but then we can do some approximations. So two types of approximation. The first one is a so-called tile low rank or TLR approximation. On the left here, we have a representation of the covariance matrix sigma, where you see these different tiles. Those are all dense. On the right here, you have this tile low rank approximation. So typically on the diagonal, we use the dense version. These are here, but below the diagonal, we can do some compression. So we take enough diagonal time, we compress it through a singular value decomposition, a low rank approximation. So we reduce basically the dimension of what has to be stored, and then the complexity of future operation, the Cholesky factorization. And we can do this compression differently for different tiles. So some tiles may need a higher rank, some other can have a very low rank, and so a very strong approximation of the tile. A second type of approximation is to change the precision. So this is about multi and mixed precision computational statistics. You know, most computation on software, for example, in R for statistician, are done in double precision with 64-bit. But for many applications, this might be overkill. So, for example, if you're interested in temperature, I mean, you don't need to have a 10-digit after the temperature. Of course, you have to make sure that in the operation that you do, you still have enough precision. But the idea is that this could be reduced to either single precision, so with 32-bit, or even half precision with 16-bit. And the idea is to accelerate the computation and also to have less information to store. Now, you could do all computation in single precision, all in half, but you can, this is often called multi-precision, but you could also mix the precision. So that's what we're doing on that covariance matrix. Some tiles will remain dense in double precision, DPs for double precision. These are the gray one. Some in blue will be in single precision, and some in green will be in half precision. There's a way to choose the precision of each tile. In fact, mathematicians have studied this kind of problem. For example, Nick Hayam in the UK has a number of papers on this idea of mixed precision and some theorems with certain guarantees and algorithm to choose which precision to give to each tile. We have developed also an R package for this. It's called MPCR that will do exactly this. It's going to, if you use the package, which now is finally on trend, but also you can download on this GitHub, you can change the precision from double to single and half, and you can do this kind of mixed precision tile-based operation. And this is not restricted to this spatial data science. So you can use in other fields of statistics. You can use it on your own problems or computations. And I think really there's an opportunity to think more in that direction on how changing the precision in the computation for certain problem can be used to speed up basically the computations. Here you have two plots with different operation. Cholesky is this group here with different size of matrices. The one in orange is about 15,000 by 15,000. And what is plotted is the speed up. For example, you compute R in double precision and the package in double precision. Because the package uses very optimized libraries, the speed up is about 500 for Cholesky factorization. R by default doesn't have single precision. So if you compare R double precision with the package in single precision, then you have another factor of 2. So it's about 1,000 times faster for the Cholesky factorization of this 15,000 by 15,000 matrix. So in the software ExaGeoStat, you can mix all those, right? So you have first the exact dense double precision. Now you keep everything dense, but you can change the precision in different ways. I think the best is this Nick Hayam adaptive version. And then you can do also this tile rank approximation on top of mixing the precision. So this is really the most reckless version of approximation, I would say, on this covariance matrix. All right, so we have an R version of the software, ExaGeoStatR, that people can use. This is to give you some idea about the timeline of the development of the software. Of course, it was not just a one-week project. It has taken a number of years, and little by little, we improved things and adapted to new ideas and technologies. If you use to these competitors, either fields or GeoR, to do spatial data science, to compare with these packages, you see, so here, what is plotted as a function of the number of location n, the execution time per iteration for that likelihood. The size for these classical packages stop at around 20,000 location, whereas we can go much further with the ExaGeoStat package. And if you look relatively in this plot, compared to field, ExaGeoStat is about 30 times faster, compared to GeoR about 100 times faster. So I have many other experiments that I will skip here. Just going back to this sea surface temperature I had at the very beginning. Now the idea is that for every day we can very quickly fill these empty areas, and it would look like that. Okay. So now comes the third part that describe a little bit this competition that we organize. So really, the idea was to evaluate and rank different approximation methods. So we as I mentioned earlier, we simulated this very large data set. They have 1 million locations each for each of the 3 competitions from 2021, 2022, and 2023 that again can be used as benchmarking data and that you can download and are publicly available. We have also associated papers that describe how the data were generated, what was the main finding from the competition, the main method that were used. We report also the exact MLEs. So if you have 1 million by 1 million covariance matrix, you can estimate this parameter for this data set, and we have the exact MLE. So if you come up with an approximate method, you can see how far your approximated MLE would be from the one you can get from exact computation, and also on other problem of prediction at new location. So the first competition was mainly on Gaussian and non-Gaussian problems. For example, if you want to do estimation for Gaussian processes based on 90,000 locations. And then we had some larger cases also, and doing prediction at new locations. And we had a good turnout, so about 29 teams signed up for the competition. In the end, it's still challenging, people sign up, but once they realize that they get 1 million location, one size, a data set of size 1 million, well, there are a lot of problems that appear. So some gave up, but eventually 21 teams submitted their result. And we have, again, a paper that compares those different results. In 2022, we extended to some non-stationary models, some space-time model, and also some bivariate model. We ran this on the Kaggle machine learning platform to make things a bit more attractive. And last year, we ran another competition where we changed the design of the location, for example, to mimic satellite paths and see if some method were better than other to do that. And also, instead of asking just for point prediction, we asked for confidence intervals or prediction intervals in this spatial setting. So that's to give you some idea about this competition. Again, if you want to read more about this, we have 3 associated papers for each of these 3 competitions. Okay, so in the remaining time, I will tell you a little bit about the latest project we've been working on, namely to build these climate emulators. So this, what I'm going to describe, in fact, relies on this idea of mixed precision and using this runtime system to optimize the computation on supercomputer. So the paper that described the result I will present is called Boosting Earth System Model Outputs and Saving Petabytes in the Storage Using Exascale Climate Emulators. This is my collaborator on this project. And the paper was selected as one of the 3 finalists for the Gordon Bell Prize in Climate Modeling. This will be awarded in November this year. So we're going to go to the conference in Atlanta and present more details about this result. But I wanted to tell you a little bit of the story because it's linked to what I have presented earlier. So the idea is, well, how do we understand the climate, whether it's changing and what's happening with our climate on Earth? Well, one way is just wait and let time go, right? So we observe over days and years, and we'll see in some years if it has changed more or less. The other is to basically run simulation because we don't know in advance how this will behave. So the current state of the art are called Earth System Models, or ESMs. They are basically climate models. They are based on PDEs, on physics, essentially Navier-Stokes type of equation that will describe the state of the ocean, the atmosphere, ice, sea ice, all mixed together, very complex that you have to run on supercomputer. And unfortunately, it's very computationally demanding. So to solve, so you start in the past, you solve these PDEs forward in time. If you want a high resolution in space and also in time, possibly, well, this can take weeks or months even to have one run. And one run is like you have one observation. You have one observation of how the climate will change. And of course, you want to have more because you want to not just have a result based on one observation, you want to quantify uncertainty as well. But unfortunately, you cannot afford many runs. So typically, you have 2, 3, 5, this order. So this ESMs, they are fundamental in the assessment report from the IPCC. I mean, all this conclusion about the climate changing and to what extent rely very much on this ESM. So they are demanding computationally, but there's an additional problem that comes up, which is the storage of the result. So these are in fact petabyte scale type of storage that means you need a lot of memory, and this has a cost. So these centers, like the National Center of Atmospheric Research in Boulder, Colorado, I mean, they have to spend a lot of money on this storage, and this has become a real problem because at the next assessment report, what do? You throw away the old data, but you would like still to keep, and you want higher and higher resolution. So in fact, the problem is just becoming worse and worse. So climate emulators are basically a complement to the output of these system models. The idea is that they are stochastic models that are meant to mimic the behavior of these ESMs based on simulated data from the ESM. So from a few number of runs, we want to build this climate emulator. Once we have built it, we can simulate from it possibly an infinite number of emulation fairly quickly, and this can be used to quantify the uncertainties. So climate emulator has a history, and many people have thought about how to build emulators. What is plotted here is horizontally the spatial resolution. So these are about global models. So think about the sphere. On the sphere, you have a spatial resolution. So here it's going from 400 kilometers down to about 3 kilometers. And vertically, what is plotted is the computational complexity scaling, so on a log scale. And what has been represented here in green are basically existing models. So in this green square is this gray squares with a number refer to some publication of existing climate model. And basically globally, the finest resolution is still about 100 kilometers of the emulator, not the climate model. And also some of these models make some assumptions that are somewhat restrictive, for example, for axial symmetry. So this type of scaling here are for the one that assume axial symmetry on the sphere. This means that you have non-stationarity over latitude, but at a fixed latitude over longitude, you have stationarity. So this is somewhat restrictive. It reduces the computation. So if you want really anisotropic model, these are the curves and the type of scaling. So what we want to do in this project is to address this and basically increase the resolution down to, so these 4 green stars go up to about 3 kilometers on the sphere. So here are some of the contributions that have come from the model we have proposed. So we have a factor of 28x in space and more than 8,000x in time compared to other existing emulators. We're using the spherical harmonic transformer SHT on the sphere to model these anisotropies. And basically the finest scale that we reach is about 54 million spatial location on the sphere. This is called ultra high spatial resolution in climate science. And this means about 3.5 kilometers. And this also at an hourly resolution in time. So for 1 year of data, this represents 477 billion space-time observation. So now the idea is that once you train this emulator, basically at any time you can simulate a number of emulations, and you're saving all this storage. You don't need to save the result. You can use it to do some analysis, and then you can just erase it. And if in 1 year you need it again, you resimulate. It will not be exactly the same, but it's meant to mimic the behavior of the ESM. So what is represented here on the left are simulation on a particular day, June 1st, 2019. On the right are the emulation from the climate model. Of course, they will not be exactly the same. Huh? They have to be statistically similar. Now, how we do that? Well, we use exactly this idea of mixed precision to speed up the computation, and we use this runtime system. We use parsec in this particular case. And with this code and technique, we were able to run on 4 different GPU families. And being from Switzerland, I like to say that we went from Leonardo to the Frontier via the summit of the Alps. So Frontier is the top supercomputer here. We reach almost 1 exaflop with about 36,000 GPUs. Alps is in Switzerland. We reach about 0.7 exaflops with 7.7 thousand GPUs. We run also on Leonardo, reach about 0.2 exaflops with only 4,000 GPUs. And this is for Summit, 0.37 exaflops with 18,000 GPUs. So this is a kind of old supercomputer in the US that is being retired right now. And so the GPUs are also a bit old. All right, so here I have added a list of publications because I will make the talk available. I've done this because many of these publications are in fact in IEEE journal from HPC, so they are not the typical journal that statistician would read, but they are listed in increasing order in time. The one in red here is the one that we presented and became finalists for the Gordon Bell Prize in 2022 that Laura had mentioned in the introduction. So it was using this software ExaGeoStat. We were running on Fugaku at the time in Japan, and the communication was not so good. So, well, there's always one winner with 6 finalists here. We were not. There is this paper I highlighted in red in environmetrics that I think is good for statisticians who want to learn a bit about the software. Has a lot of code also to try out different experiment for your own data if you wish. And the last one here in red is the one that will be presented in Atlanta next month. So just to wrap up, I started to describe these 5 problems that all involve a Cholesky factorization of the covariance matrix. That's a difficult task for large data sets. So I talk a little bit about HPC, high performance computing, this idea of dynamic runtime system, a tile-based linear algebra for the covariance matrix, and approximation either with low rank tiles or mixed precision. Again, this mixed precision, we have the package that you may be interested in trying for your own application that might not be related at all to this presentation. This software ExaGeoStat eventually allowed us to run this competition for large data set. And eventually all this idea came into building this exascale climate time emulator as I presented here. The slide will be available from my website down there in red. We have also some videos from some short courses about the software if you want to learn more about it. So thank you very much for your attention, and I'm happy to take any questions. Thank you.